doing mole-to-mole conversions is nice, but we can't measure things in terms of moles because it's a number of particles and nobody has several lifetimes to count that many particles. So we weigh things to count them. So we need to get mass in here somehow. So the chemical equation gives us relationships between moles of reactants and moles of products. This is the part we just learned about. Going from moles of one thing to moles of another thing. The relationship comes from the balanced chemical equation. But if we want to have masses, we need to start with the mass and end with the mass of the other thing. That's more useful. How do we get from mass in grams to moles? We use the molar mass. So we've learned how to do this step, and we learned how to do that step before today, and we learned how to do this step today. Now we're just going to put them together. The big picture here, the overall path is what I like to call grams to moles to grams. And you can just, when you're doing any of these stoichiometry problems and you're not sure what to do, you can kind of fall back on that. We might do some little variations on it, but it's grams to moles to grams. And so you should just say that over and over to yourself until you wake up in the middle of the night mumbling grams to moles to grams. Yeah. Then you know you've got it in your head. Okay, grams to moles to grams. Say it over and over again, just like I said, group 1A, 2A, 3A, zinc, and silver. You guys remember that now? Groups 1A, 2A, 3A, zinc, and silver. Those are the metals that do not need a Roman numeral. Everybody else does. Okay, so let's look at this. We've talked about burning things, right? So here we have octane that's in gasoline. It's combusting, it's reacting with oxygen. Remember that anytime you have a compound with carbon, hydrogen, and possibly oxygen, and it's burning, reacting with oxygen, the products are always the same, carbon dioxide and water. You know that those are the products because you memorize it. Just because. There's no reasoning it out. So our question here is, what mass of carbon dioxide is emitted by an automobile when 5.0 times 10 to the 2 grams of pure octane is burned? Okay, that could conceivably be a useful thing, right? I'm sure nobody really wants to know the answer, but you can imagine why someone might want to know. So I'm going to take the information here and I'm going to write it under my balanced chemical equation to organize. So this is grams of pure octane. Now, if this was a test question, and it's not giving us the formula for octane, how do we know which one of these things is octane? Because we know what everything else is. Exactly. This is oxygen. We know this one, carbon dioxide, and that one's water. So this guy has to be the octane. So I've got 5.0 times 10 to the 2 grams of that. And what are they asking me for? Mass of carbon dioxide. Doesn't specify the unit. We can pick the unit. Choose something easy. Gram is going to be the easiest. So question mark, grams of carbon dioxide. So I've got grams here and I've got grams here. This relationship in the chemical equation doesn't do grams. It's not 2 grams of this makes 16 grams of that. It's 2 molecules of this makes 16 molecules of that. Or 2 moles makes 16 moles. So I need to do moles in the middle. So my overall path is grams to moles to grams. So it's going to be grams of what I'm given information about, grams of C8H18, to moles of that, C8H18, to moles of the thing I want. I could go to moles of oxygen or moles of water, but they're not asking me for that, so that would be a detour. I'm just going to go straight to this one, moles of CO2. And then I want grams of CO2. Okay? Grams of what they gave you a mass of to moles of that thing to moles of the thing they're asking you about, to grams of the thing. Okay? Grams to moles to grams. In each of these arrows, we're changing one thing. In this first arrow, we're changing the unit from grams to moles, but we're still talking about octane. In the last one, we're going moles to grams, but we're still talking about carbon dioxide. In the middle, the unit stays the same, moles, but now we're changing the compound. You can only change one thing at a time. Any questions about the path?
This is like what we were doing before.
This is like what we were doing before. It's just the path is looking different. What we're doing is we're taking the process of dimensional analysis, and we've done gram to mole conversions, so that's at both ends, and we just learned how to do mole to mole conversions, and we're putting them together. Once you get this path, if you've gotten the hang of dimensional analysis, it's just a matter of writing stuff down. There's lots of little teeny tiny steps. None of the steps are really that hard. Putting them together can be a little overwhelming sometimes. But just look at it as individual steps. So I've got my path, so I'm going to start. So 5.0 times 10 to the 2 grams of C8H18. It's really important to write the chemical formula there. It is tedious, I get it. I have how many arrows? 1, 2, 3. 3 conversion factors. 1, 2, 3. Excuse me. The units in my path are the units that go on the top here. So grams of octane to moles of octane to moles of CO2 to grams of CO2. The path just tells us what to do. All we have to do is follow the path. I need this unit to go away, I divide by it. Grams of C8H18. So that unit cancels out. Here I'm going to put moles of C8H18 in the denominator, so that unit cancels out. Moles of CO2, so that cancels out. The unit that's left, grams of CO2, is what they're asking me for. All is good. I like to do the center conversion factor first because it's the easiest. How do we get numbers for this one? Balanced chemical equation. So we don't have to calculate anything, we just have to look and copy. So in front of C8H18 is the number 2. That means 2 moles of this react to form 16 moles of that. So 2 goes in front of the C8H18. 16 moles of CO2 are produced, so 16 goes up here. Okay? Now we're going to need the periodic table because these conversions involve molar masses. So we have to calculate some molar masses. So for C8H18, so that's 8 times the mass of carbon plus 18 times the mass of hydrogen. 8 times 12.01 plus 18 times 1.008. I'm getting 114.224 grams is equal to 1 mole of C8H18. Anybody else get that number? Yeah, thank you. Because I screw up sometimes. So we should always be thinking about significant figures. I tend to think of this as adding, and so, you know, we could say that that's the last significant figure. That is 5 sig figs. How many significant figures do we have in our starting number? 2. Usually, this number is going to limit the number of significant figures. So we don't really have to think too hard about this. I think it's easier because there's less thinking. I prefer to just write down all the digits my calculator gives me. At most, it's going to give you 3 decimal places. it's not going to fill up your display with numbers, so it's not like you have to worry about that. So I'm just going to write that whole thing down because it's not going to hurt anything. And then over here we need the mass of CO2, which is 44.01. But let's write that out. We'll go way up at the top. For CO2, it's 1 carbon, 12.01 grams, plus 2 times the mass of oxygen, and that ends up being 44.01 grams is equal to 1 mole of CO2. So this many grams of CO2 is equal to 1 mole of CO2. Now I multiply and divide. So you take this number times the top, like, oh, there's no number there. Oh, put a 1 there. Times the top, divide by the bottom. Times the top, divide by the bottom. Times the top, divide by the bottom. So my calculator is giving me 1541.18 and some other digits. The unit is going to be grams of CO2. I need to consider significant figures. So this has 2 sig figs. So this should end with 2 sig figs. Do not round that to 15. Okay, it's 1,541.18, blah, blah, blah. When I underline this place, I am rounding to the nearest number in that place. This is the ones, the tens, the hundreds. I'm rounding this number to the nearest 100, right? So I'm deciding, is it 1,500 or 1,600? It's closer to 1,500 because this next digit is lower. Okay, this is a really common, persistent problem, people rounding their numbers incorrectly. So some of you are good with that, and you're like, oh yeah, that's 1,500 grams of CO2. Got it. Okay, so if you keep screwing up on this, this is what you need to do. Anytime you're rounding to a place that's higher than the ones place, tens, hundreds, thousands, whatever, put in scientific notation and then round it. And then you won't accidentally change 1,500 into 15. Because we could do some fun financial transactions if you think that 15 is the same as $1,500, right? You give me $1,500 and I'll give you $15 back. And let's do that all afternoon, right? It's not the same. You understand that when it's money, but when it's grams, you'll lose your minds. It's okay. You're in good company. So if I'm putting this in scientific notation, 1.5, the decimal point always goes after the first non-zero digit. It doesn't go after the 5, it goes after the 1. 1.5, and because we're putting this in scientific notation, we can stop wherever we need to. 1.5, that's my 2 sig figs, that's all I need, times 10 to the, I'm going to do this in red. I'm moving this decimal point 1 place, 2 place, 3 places. I'm not counting from the end of the number. I'm not doing any of those other creative things. This is not a place for creativity. 1, 2, 3. So the exponent is 3. And then you ask yourself, is it a big number or a small number? 1,500. It's a big number. How does Mrs. K feel about big paychecks? Positive. The exponent is positive. Grams of CO2. So this is a good answer. This is a good answer. Any questions? Let's do another one using this same chemical equation. What mass of octane would be needed to generate 42.3 grams of water? Well, 42.3 grams of water. I'm going to write that under water in the chemical equation just to organize. 42.3 grams. That's kind of an ugly 2. Fix that. Oops. Well, let's just start over then. 42.3 grams. And what are they asking? Mass of octane. So here's my octane. Question mark. The unit is grams. So I have a starting mass and an ending mass. Yes, we're starting with the product. That's okay. The path is what? Grams to moles to moles to grams. Okay. So this time it's starting with grams of water. Grams of water to moles of water. To moles of octane to grams of octane. And that's not the right number. If you're struggling with this at all, write out the path. When you send me a picture of your work and you're asking me questions, I want to see that you wrote out the path. Maybe you don't believe me, but writing the path is really the key. Makes so much more sense if you have that in front of you. So I see I have 3 fractions. I'm starting with my number, 42.3 grams of water. 3 fractions. So the first one is going to have moles of water on top. The next one is going to have moles of octane. And the last one is going to have grams of octane. Just writing down the path. Units, I put these in the denominator to cancel out. Okay? Units come first. They tell me where to put the numbers, whether I'm multiplying or dividing. I don't have to think about that. So this middle one, the mole-to-mole ratio, how many moles of octane? 2. From the balanced chemical equation. How many moles of water? 18. It's just right up here. 18 moles of water come from 2 moles of octane. Then I need molar masses. Well, in the previous problem, we calculated the molar mass of octane. It hasn't changed since then, so I'm just going to write it down. 114.224. And then we need the molar mass of water. So for water, 2 times 1.008 plus 16 is 18.016. Grams of water is equal to 1 mole of water. So here in this ratio between moles of water and grams of water, 1 mole of water weighs 18.016 grams. Any questions? Going a little faster. If you need it slow, you can watch it again on YouTube. YouTube instructors are so patient, they'll do it over and over and over for you. It's awesome. Make use of that. So now it's just calculation. This number times the top, divide by the bottom, times the top, divide by the bottom, times the top, divide by the bottom. You don't have to write anything down. You don't have to remember anything. You just follow the pattern. So 42.3 divided by 18.016 times 2 divided by 18 times 114.224 equals, how many significant figures should my answer have? It should have 3. I started with 3. In most of these problems, it's going to be the starting number that limits, and it's all multiplication, so you don't have to really worry about anything in the middle there. So 29.7, that's my 3. I'm going to write down 2 more digits. My unit is grams of octane. Here I'm rounding in the tenths place, to the right of the decimal point. People don't screw this one up, so we don't need scientific notation. But I look at the next digit, it's a 9, so that means I have to round this 7 up, and I'm going to say this is 29.8 grams of octane. Questions? Yes? That's a good question. Can I just do this, and divide by this? I don't recommend that, because what students have a tendency to do is they multiply this times this times this times this, and then they divide by this times this. And you have to use parentheses in order for that to come out right. So I really think it's better to just go left to right, top and bottom. This times that, divide by that, times that, divide by that, times that, divide by that. That always works. And feel free to skip the ones. You know, if you multiply and divide by 1, it doesn't change anything. So go ahead and skip those if you want to skip them. I do. I say that I'm multiplying by them, but I actually don't push the buttons on the calculator. Nobody's up here watching. So definitely do that. But you can do what you're asking, but I don't recommend it. Any other questions? Let's do another one. These are like at the core of chemistry, these types of calculations. So there's lots of examples here. Magnesium hydroxide, the active ingredient in milk of magnesia, neutralizes stomach acid, which is mostly HCl, according to this reaction. Okay, do we need all those words up there? No, that's backstory. This is the important part. How much HCl in grams can be neutralized by 5.50 grams of magnesium hydroxide? So we need this number, and we need the question, and we need our balanced chemical equation. So I'm going to write 5.50 grams under the formula for magnesium hydroxide, because I have that many grams of this thing. And then the question, how much HCl in grams? So here's HCl. So this is my question, and the unit I want there is grams. So now we have a path, grams to moles to moles to grams. So grams of magnesium hydroxide to moles of magnesium hydroxide to moles of HCl to grams of HCl. Grams to moles to moles to grams. 5.50 grams of magnesium hydroxide times, the next unit is moles of magnesium hydroxide, times, the next unit is moles of HCl, times, the next unit is grams of HCl. Grams to moles to moles to grams, grams to moles to moles to grams. It's just the path spread out with multiplication signs. This unit comes to the bottom, grams of MgOH2, moles of magnesium hydroxide, moles of HCl. So those cancel out. We need 2 molar masses and 1 mole ratio. The mole ratio is the easiest, so I like to start with that one. We look at the balanced chemical equation. 2 moles of HCl, 2 moles of HCl, 1 mole of magnesium hydroxide. And we need to calculate some molar masses. So for magnesium hydroxide, 24.31. Yeah. So magnesium is 24.31. We've got one of those. So 24.31 grams. How many oxygens? 2. Because we have 2 hydroxides. So we've got 2 oxygens and we've got 2 hydrogens. You really should write this out, because if you do this a little wrong, like maybe you didn't notice that there were 2 oxygens here and so you left that out, and you put the numbers in, you come up with the wrong answer. If you've written out everything you've done, and Mastering Chemistry says incorrect, try again, you can go back and look at this and go through it in your mind and check and see, oh, that's what I forgot, and fix it without starting over. Just another thing about Mastering Chemistry. I can see all your answers, and I've seen some of you that you've put the same number in there 10 times. Okay, if it was wrong the first time, it's going to be wrong all the other times. It's not going to change its mind. You know what the definition of insanity is doing? Yeah, doing the same thing over and over again, expecting a different result. Don't be insane, okay? If you put it in and it's not right, don't use that one again. And you can have it show you your answers so that you can make sure not to repeat yourself. There's a little thing that says My Answers, and you can go and it'll show you all your answers. Okay? So don't be insane. At least not about this. If you want to be insane about something else, I guess that's up to you. Anyway, 24.31. See, I lost the decimal point. 0.31 plus 2 times 16 plus 2 times 1.08, 58.326 grams is equal to 1 mole of this. So 1 mole, and I get 58.326 grams down there. HCl, I'll do it right here in the middle. HCl, there's 1 hydrogen and 1 chlorine. And so that's 36.458 grams. So 36.458 grams per 1 mole. Now we're just going to go across. 5.5, I don't like to multiply by 1. Divide by 58.326. Times 2, I don't like to divide by 1. Times 36.458. Again, I'm not going to divide by 1, but you can. It won't change anything. Calculator says 6.8758 grams. 3 sig figs here, 3 sig figs in the answer. All of these should have more. That's why you don't want to round your molar masses too much. If you round this to 36, it's going to screw things up. Use at least a couple decimal places here. This is exact. So I'm going to keep that. It's on the right side of the decimal point. I don't have to worry about changing the value. And so there we go. 5.50 grams of magnesium hydroxide can neutralize 6.88 grams of HCl. And I understand nobody cares, but there it is. We did the problem. Any questions? Another one? Good grief. This was a little different, though. So this is what happens in 3A, Chem 3A. I'm doing lots of different variations of the same problem. So we've done 2 reactants, we've done a reactant and a product, we've done a product and a reactant, and now this one's got kilograms in it. Okay? So let's just take a deep breath and do it. Because there could be an example, or it wouldn't be an example. There could be a problem like this on a test. Okay, so one component of acid rain is sulfuric acid, which forms when SO2, a pollutant, reacts with oxygen and rainwater according to the following reaction. All that's backstory. We need the reaction. Assuming that there's more than enough O2 and H2O, how much H2SO4 in kilograms forms from 2.6 times 10 to the third kilograms of SO2? Well, let's organize. So SO2, we've got 2.6 times 10 to the third kilograms, and they're asking for mass of sulfuric acid in kilograms. Okay? What's our path? Grams to moles to moles to grams. Grams of what they gave us a number for, grams of SO2, to moles of SO2, to moles of what they're asking for, H2SO4, to grams of H2SO4. But this isn't going to quite work for this problem, is it? Because we've got a mass in kilograms, and they're asking us to find a mass in kilograms. Can we convert kilograms to grams? Sure we can. So this one we're going to have to add on. There's different ways to approach doing this problem. I'm going to do what I think is the most straightforward for you. So we're going to start with kilograms of SO2, convert it to grams. And then at the end, they're asking us for kilograms of sulfuric acid, so we have to convert back from grams to kilograms. There's a lot of arrows. It's okay. It's okay, we can do this. 1, 2, 3, 4, 5 arrows. But we've got our path. It's just follow the pattern. It's just going to be a longer walk. We're going to have to write smaller to fit it on the page. 2.6 times 10 to the third kilograms of SO2. And I'm going to convert this to grams of SO2. And then I'm going to convert it to moles of SO2. And then moles of sulfuric acid, H2SO4. And then grams of H2SO4. And then kilograms of H2SO4. We don't have any room for the answer, but that's okay. Sometimes I get bored starting at this end and putting the numbers on, and so I'll start at the back end and work backwards just to make it more interesting. Doesn't help much, but whatever. So I need to divide by that, so that'll cancel out. And here, I'm going to divide by H2SO4 moles. This is moles of SO2. And this is grams of SO2 and kilograms of SO2. Did you think you'd be doing something like this a week and a half ago? Ah! So we need relationships for these numbers. Let's start with the middle one because that's the easiest. 2 moles of SO2 will make 2 moles of H2SO4. So 2 and 2. Could you cancel those out? Sure. Write them in there, though, before you cancel them out. You can also just leave them in there. Doesn't matter. Then I've got grams and kilograms. Kilo means 10 to the what? 10 to the plus 3. So kilos in the denominator. I'm going to put what it means in the numerator. 1 times 10 to the third grams is 1 kilogram. I've got another conversion like that over here, but I've got kilo on top, so this time 10 to the 3 goes in the bottom. 1 kilogram is 1 times 10 to the third grams. You might also recognize that those numbers are going to cancel themselves out. If you recognize that, fine, do it. If you don't, punch it through on your calculator and it'll take care of itself. Now we need molar masses. So we need a molar mass for SO2 and one for H2SO4. So for SO2, we've got sulfur plus 2 oxygens. 32.07 plus 2 times 16, 64.07. So 1 mole of SO2, 64.07 grams of SO2. So this is like the minimum I want you to write down. I left out the grams, I left out the grams equals moles of SO2. This is like the bare minimum. But it's written down so I can see how I got the number. If I screwed up, I can go back and figure out how. And then H2SO4, 2 times 1.008 plus 32.07 plus 4 times 16 equals, so 2 times 1.008 plus 32.07 plus 4 times 16 equals 98.086. So 98.086 grams of sulfuric acid to 1 mole. Any questions? Okay, start at the left and move to the right. 2.6 EE3 times 1 EE3 divided by 64.07 times 2 divided by 2 times 98.086 divided by 1 EE3 equals this is telling me 3980.39 kilograms. Looking at this number, I should have 2 significant figures. First of all, did anybody else get that number? Thank you. That's a big number, isn't it? Well, what kind of a number did we start with? A big number. So it's very reasonable to end up with a big number. Here we're rounding in the thousands place. No, hundreds place. We're rounding to the left of the decimal point, so we need to be careful. So if we round it without putting it in scientific notation, we're going to end up with 4,000 kilograms. But it's supposed to have 2 significant figures, right? This place is supposed to be significant. That's tricky to make clear without using scientific notation. If we put this in scientific notation, remove the decimal point 1, 2, 3 places over here, and it's going to be 4.0 times 10 to the 3 kilograms. In scientific notation, it's easy to indicate that this 0 is significant. These zeros are not considered significant figures, but the first one is. In decimal notation, that's tricky. So this is the best answer. Any questions? Yeah.
In my calculator, I got the same numbers. I just got it already as 3.98.
So the decimal point was in a different place?
Yeah.
Okay. So what happened, most likely, is when you entered this number, you didn't communicate correctly with your calculator. So some of you are still doing 1 times 10 caret 3. So your calculator doesn't understand that you're dividing by all of that, and you end up multiplying by 1,000, or some other sort of thing. It's most likely an issue with scientific notation.
So I answered 1E3 on it.
And it still came up?
I think you have to put a parentheses, but I got the same thing. I put parentheses on each one. I was going to enter the top and the bottom of parentheses.
Let's look at that during the break, okay? Anybody else have a question?